The reason that we as humans care about climate change is that it affects not just the temperature, but a whole bunch of other things that we care about. It affects soil moisture, which in turn affects our ability to grow the things that we eat. It affects cloud cover. It affects rainfall patterns. It increases drought risk in some regions and decreases it in other regions.
Understanding our changing climate on a planet with incredibly complex and interconnected systems is a massive scientific undertaking. And climate scientists like Kate Marvel are using the data collected by satellites from around the world to improve the power of climate models. If we want to make better decisions about where we live, understand the changing impacts of hurricanes, or improve predictions of fire seasons, we need evolving climate models.
We don't have any observations from the year 2050, from the year 2100, but we can use our best knowledge of physics and chemistry and how the Earth system works in order to look at the impact of different emissions trajectories, different policy scenarios.
Climate models provide a view into our future, from our globe to our own communities.
As models advance, as they're tasked with predicting the nature of the weather and the clouds over smaller and smaller scales, they're being asked tougher questions like, well, what kind of clouds are happening over those small scales and how often? And how heavily are they raining?
We expect, roughly on really, really large scales, climate change is making wet regions wetter and dry regions drier. But at the same time, it's shifting the circulation of the atmosphere. So the locations on a very, very large scale of those wet and dry regions are changing.
Climate models are composed of lots of different calculations on the different behaviors of our atmosphere, our land, and our oceans. To accurately represent the natural world, they need massive amounts of satellite data over decades from NASA's Earth observation fleet and its partners around the world. Satellites like the Global Precipitation Measurement Mission provide valuable rainfall data on daily to seasonal timescales for the past 20 years. And it's that information, along with a suite of other data, that go into climate model development.
Currently, GPM microimager radiance data are used to generate initial states of NASA climate models and to guide climate model solutions to be close to real states by applying data assimilation techniques.
Data assimilation is the process of combining many different sources of Earth observations into models to improve how we represent the Earth system.
Assimilating GPM microimager data improved intensity and locations of storms and precipitation calculated by the climate models.
And once a climate model is developed, it's tested over and over because, well,
all models are wrong, but some models are useful. So they're always going to be incomplete. They're always going to be a not exact representation of the real world. But we want to make sure that they are capturing important aspects of the Earth so that we can treat them as credible going forward.
Typically what happens is when you modify one part of the climate model, other parts accidentally change. It's kind of like the whack-a-mole game. By hitting it down, we're improving it, we're killing the error, we're decreasing the problem existing in the model, but another area pops up.
And that is why NASA observations of the Earth from space, the air, and the ground are critical to understanding how our Earth system works. Observations help improve the modeling for our future here on Earth with new capabilities to expand our knowledge.
NASA is launching satellites and coordinating missions like GPM, giving us that long-term, really accurate satellite record of what's been going on, not just of the temperature rising, but of various aspects of the climate changing. So precipitation and cloud cover and soil moisture and a whole bunch of different climate variables that people care about.
Continuing key observations of the Earth is really important to see how our atmosphere, land, and oceans are changing over time. A long-term record combined with cutting-edge observations from the new NASA Earth System Observatory will continue to push boundaries to better understand our ever-changing Earth.